Okay, in this video, we're going to take a look at consumer surplus as a definite integral. We're going to see the formula and where it comes from in terms of Riemann sums. So a couple of little definitions. The demand curve is given here. P is d of x, is the price per unit, and that's going to be very important, per unit that consumers are willing to pay for x units of a good. And you need to remember that x doesn't always need to be a whole number. For example, we could be talking about dollars per liter of gasoline, or dollars per kilogram of flour, or something like that. So x, when we say units, it doesn't have to be like, 5 televisions, where you can't have 4.5 televisions or something. It can be in terms of some sort of measurement, like liters or kilograms or whatever, that doesn't need to be a whole number. Then the consumer surplus here is the total benefit. And again, that word total is going to be very important. Total benefit to consumers when they pay a price P naught or P0, but would have been willing to pay a higher price. And so the formula for consumer surplus is usually given in some variation of this definite integral, where we're talking about x0 here, x0 being also sometimes called q0. That is the x value that gives us our price P naught that we're talking about. So d of x0 is equal to P0. So the integral from 0 to x naught of d of x minus P0 dx, which means that the consumer surplus is an area. And if we look in terms of our vertical slicing, we're talking about top curve minus bottom curve on this area, on this interval, which would give us this area here. So let's take a look at why this formula makes sense for consumer surplus in terms of an area. So if we look at this graph again here, then we have to think about, for a single consumer, what is the benefit? The benefit for a single consumer, and we're looking for total eventually, but let's start out for a single consumer, is the price that they were willing to pay minus the price they paid. And these prices are per unit. These are unit prices. So that means we need to multiply these prices times the number of units. So for example, if the price is set at P0, then anybody who was willing to pay more than P0 is receiving a benefit, right? So anybody along this part of the demand curve here, anybody who would only pay a lower price, well, obviously they're not receiving a benefit if they have to pay P0. So along here, let's consider, for example, if we were just to take somebody at this point over here, they were willing to pay, so let's call this x1. They were willing to pay this price up here, d of x1. But they only had to pay P0. So they're receiving a benefit of this, right? So their benefit for this one consumer is d of x1 minus P0, right? That is their benefit. D of x1 minus P0. But that's just one consumer, right? We want the total over everybody. So we're going to imagine that we're taking everybody from who's receiving a benefit, right? So everybody from 0 to x naught, which means we're looking on this interval 0 to x0 or q0 if you like calling the quantities q, which, if we're looking in terms of the definite integral, might be nice to label as sort of an a-b value. And then the quantity, well, how much, right? If we imagine that we're looking for a total here, then let's say that we're going to make an approximation to start with. We're going to say that everybody sort of on this part of the curve now in orange, let's make the approximation that they were also, for the moment, only willing to pay this d of x1. So let's flatten that curve for a little second here. And then what is the total number of units then that they are willing to pay? Well, that total number of units is, well, what? Between 0 and x1. So that is that distance here. That's our number of units. And if we imagine sort of doing this over and over again, right, we could say the same thing for x2 and x3. In fact, we could keep on doing that n times. And if we divided those into n equal intervals, then we would say that delta x could be our x0 minus 0 over n, which is x0 over n, which is b minus a over n. That would be the width of that interval here, delta x. So for consumers in that first interval, the price, the benefit that they are willing to pay, right, was d of x1 minus the price that they actually paid times the number of units, which we can call delta x. And then we're going to continue doing that same sort of thing for the next group. So at x2, they would be willing to pay, right, a consumer here would be willing to pay d of x2. And d of x2, we're going to make the same kind of approximation that everybody between those values, let's approximate here and say that they were also willing to pay d of x2. So that value here is d of x2. And so their benefit is, again, it's a subtraction. It's d of x2 minus p0. That's a price per unit, so times the number of units, delta x. And so to that first group, we would need to add d of x2 minus p0. So there's their benefit times the number of units plus, and we'd have to keep on going, right? So we could say that the consumer surplus is approximately, right, because we're making approximations here, these orange bits here, we're making approximations that everybody in that little subinterval is willing to pay the same price. It's approximately, well, we can write this as a Riemann sum. This is the sum from I equals 1 to n, and if we look through in our sum here, the only thing that's changing is the interval, the subscript, right? The d of x1, x2, x3, etc. So this would be d of xi minus p0 times the number of units, the incremental number of units that they're willing to pay. And obviously this is not the final answer that we want. We want to take the limit as n goes to infinity of this, right? We want to divide this not into just n rectangles, but infinitely many rectangles so that we don't have to make these approximations. And so our actual consumer surplus is going to be the limit as n goes to infinity of this sum, which we are probably already recognizing as a Riemann sum type of formula. And if we have the limit as n goes to infinity of a Riemann sum, then we have a definite integral. And that definite integral is going to be on our interval here, a to b, or from 0 to x naught. So the integral from 0 to x naught of our function d of x minus our other function, which is the straight line p0 times dx. So there is consumer surplus explained in terms of Riemann sums and why it is represented by the area on a demand curve graph.